Washington State University. Go Cougs!
As I said, OpenMP is like a open standard for multi-threading. Okay, and so there is a syntax that you have to stick to. It's a library that you can basically when you compile, you just specify an option and it will link it. The OpenMP runtime system will be linked to your C program or your Fortran or your Python or whatever you have. Okay, so the main construct that we will use for OpenMP programming is this pragma, pound pragma. Basically, it says that I have an OpenMP directive coming. Okay, so once you see an example that will make sense, you want to be including omp.h, okay, for your C program to compile. So the class that we'll be using essentially is pragma omp parallel. So basically, if you look at this, pragma omp says that I have an OpenMP line instruction in this line of code. Okay, and then I say here is a parallel. I'm starting a new parallel section of my code, and the number of threads I want to assign to this to execute this parallel block or this parallel region of my code is whatever I specify in the thread count variable. So if I want to say, in this section I say for this code I want to highlight this and say this is a for loop, this is a region that I want to parallelize. So then I'll put pragma omp parallel number of threads that I want to execute before that, and that means that that for loop will now execute with as many threads as you specified here.
Where's the thread count?
The thread count is coming from the user typically, or you can default it to whatever you want in the code. Typically we want to use it, basically have the user specify number of threads. You know the architecture of the system that you're using. If I have a single node with 8 cores, I will specify up to 8 threads, which makes sense because I don't want to oversubscribe the cores. If I have 16 threads running on 8 cores, that means each core will map to 2 threads and then they will have to do time sharing. Each one will get only 50% of the time, right? That's no good for parallelism. We want to make sure each thread kind of gets basically one full course time. Yeah. Yes. Oh, the number of, so are you asking if the number of threads be dynamic? It can be, but yeah, so it can be. In theory, yes, it can be. In practice, however, you are limited by the number of physical cores you have in your system. So like I said, if you have 8 cores, I can run 1,000 threads on 8 cores, but they will all be doing time sharing. So you will essentially not see the speed up that you would be expecting. So we want to limit or cap the number of threads we want to be using to the number of cores you have, physical cores, right, to expect any real speed up. On the other hand, if you think threads are not going to be active all the time, 50% of the time they expect to be active, then I'll just by sheer probability, I'll say if 2 threads are mapped to a single core, they can interleave themselves so that you use 100% of the CPU time. That's a throughput problem. We can do that, right? But in most cases, we want to cap the number of threads to the number of physical cores. Okay. Okay. Great. So we talked of this picture of having a master process, and any new thread that gets spawned off from there on, we will refer to them as worker threads, right? But actually the master process is also thread number 0. It will also participate in the computation. It's not like the master is sitting and just discharging workload to the threads. The master can actually participate as one of the P threads you have in the system. Okay, that's how it is. Okay. So these are some minor details. Basically, we will include openmp.h, and maybe I should go to the hello world case. Yeah, so I think it's much easier if I just look at this one piece of code. So so basically here is a C code, but we have inserted a few lines here and there to make it multi-threaded. Okay, so this is simple hello world code in C. It calls a hello function, and hello function all it does is basically do a print. So the main function takes as arguments, now that we want to parallelize this program, we want to specify the number of threads from the user. Typically the user provides the number of threads as a program argument. Okay? And then you load that up into this variable called thread count and use that thread count to initialize the number of threads for any given parallel region. Here I say the call to the hello function, that is a parallel region, a region that can be executed concurrently. So what you do is you put a pragma OMP parallel, which means whatever is that block of code that follows it is a parallel region, which means after this hello function is executed, when you are here right after that, all the threads have done their job, completed, and you are back to the master thread here. Okay? So basically if you start from your main function, it's only the master thread that's alive until this point, right? And then the worker threads along with the master thread, they are active in this region. And then after you're done with that region, parallel region, you're back to your master thread of execution. Now let's look into what happens in hello. Well, hello is a simple printf, but multiple threads are calling, right? All the threads you mentioned or specified, p threads, those threads are all active in this region, right? So they will all be doing this printf. So we want to essentially say how many threads are there. So there are basic OpenMP queries that we can use to understand I am inside a parallel region, meaning an OpenMP region. How many or what is my thread ID? I am a thread executing this line of code. What is my ID, my thread number in the entire space of all the threads I have, right? And I also want to know what is the overall number of threads I have in my group. So for that you have these two functions. OMP get thread num means tell me what my ID is as a thread. OMP get num threads means tell me the number of threads in my entire group including myself. Okay? So if you do hello world, you say hello from this particular thread ID, because you know my thread ID is my rank. Typically the term rank is used to refer to the ID of the thread. So threads are numbered, right? So if I have 8 threads will be numbered from 0 through 7. The master thread will be always 0. Any new threads that you create up until 8 will have IDs from 1 through 7. Okay? So who is my ID? I could be any of those threads, right? So basically this printf says which is my rank, who is, so that you know which thread is printing this message, and out of a total of these many threads, they will all print the same thread count, but their IDs will be different. In fact, that's right. Those are supported by the OpenMP environment, and so the runtime system that's associated with the OpenMP library will identify which thread gets which number and basically give you this. So yeah, go ahead. Uh-huh. Yes, so the join here is implicit, you don't have to specify it. Yeah, you can do it multiple times, yes. So basically what this means is, you know, the master thread is always active, right? The moment you open up this pound pragma OMP region, that becomes a parallel region. And then all the threads, whenever you specify, will be active in this region. As soon as that region gets out, really you're back to the master thread. Later on, you can again initiate another region with different number of threads if you want. Yeah, so if I say I'm going to execute this OMP parallel num threads with 8 threads here, all the 8 threads have to complete before I can get to this line. So they all have to execute the region, and then there is a join. This is like a wall, barrier, right? Until all those finish, you don't get back to the master thread. We don't have to have any code. So it's implied, it's implicit in that. It's taken care of. Okay. So I'll actually write code here. Yeah. Yeah, great question. So actually I'm getting to the scope right now. Okay. So let's look at this code as an example, or let me go to the loop serial, and this is something that you are welcome to open at this stage, since we might as well do this. So if you all open the loop-serial.c, it's a serial code, and just to tell you what this code does, it's very simple. It's going to execute n number of iterations using p threads. These n and p, the number of iterations and the number of threads, we as users, when we run, should specify from the command prompt, from the console. Okay, that's the usage. Okay. So if you look at this code, really we want to take the first argument, interpret it as the number of iterations. I call it the number of loops here, and then the number of threads, that's p, I'm setting it to this variable called p. Okay, that's what has happened so far. Once we have n and p, meaning the number of loops, number of iterations, and the number of threads, this is a serial code as of now, right? So here is my loop that basically executes whatever we want to do for n number of times. Okay. Now I want to parallelize this. So what we will do is we will specify pragma OMP parallel. Okay. Now this is not any kind of, this region that we want to parallelize is not any arbitrary piece of code, but it's a for loop, right? And OpenMP environment, the runtime system, has internal support to parallelize a for loop. So we will not stop here. We'll say pragma OMP parallel, and we'll follow it up with saying for. What I'm trying to parallelize now is a for loop, which means the scope would be the for loop, right? This is my parallel region from here to there. Once the for loop completes, we are back to the master thread here. Okay. So let's ignore the for loop. We'll come back to it later. So far this is a main function code. Everything is executing on the master thread. Okay. Now I want to, let's say there is this hello function or some function f. Okay. Now if I want to parallelize this some function, let's say maybe there is multiple functions, maybe there is f1, maybe there is f2, right, multiple lines of code. Okay. Now if I want to parallelize this piece of code, these need not be any for loop, right? These are function calls, right, arbitrary lines of functions that you have written. Then I basically want to highlight this region and say this would be a parallel region. So to do that, I say pragma OMP parallel. Okay. Now I stop there because it's not a for loop or anything. I say, it's just saying it's a for loop, and then I put braces to specify that block. So whatever happens inside this block becomes my parallel region. So this is the start of my parallel region, and this is the end of my parallel region. Okay. So here we are not saying one thread will execute f, another thread will execute f1. We are not saying that. Just make sure you understand that. What we are saying is each thread will execute f, f1, f2 in that order, and then pick up the next. I mean, that's it. There is no loop here. So yeah, each thread, if I have like 8 threads, each of those 8 threads will have an independent execution of f, f1, and f2. Okay, that's what we are doing. There will be 8 such or p such executions if we initiate p threads. And how do you specify the number of threads? There is actually multiple ways of doing it. One way is to specify the num threads like we did here. I can say the number of threads I want to use for this particular region is p. Okay. That is this, then that many threads will be active to execute that region. There is also an alternative way of doing it. Instead of specifying it here, okay, I can specify pragma OMP. Oh, sorry, it's not pragma OMP. It's OMP set num threads to P. So you basically call a function, and this function execution is happening from the master thread, and it's saying I want to set the number of threads to P, but those P threads will be active only when I enter a parallel region. So if let's say I have some other lines of code here, some bunch of lines here, right? By the way, none of this code will compile now because that's okay. So what I've done here is I've set the number of threads in anticipation that there will be a parallel region in the future, and at that time I want to use these many number of threads. Okay, it's like a global setting right now. So I don't have to worry about where I set it as long as I do it sometime before, right? It gives me flexibility there, but it will be active until the time I reset it or change it to a different value. Yes?
Yeah, I have a question related to that different value. I'm assuming it's the case that sometimes not if you define later on in subset code what your threads are that will overwrite that one.
Yes.
And then you
It will override that one as long as it's happening from the master code, from the master thread. But let's say inside, I mean, let's say we did this, right? And we entered some function f. And inside that function f, remember, is being executed by all the P threads. So there are P copies of function f executing simultaneously. Let's say one of those threads does another OMP set, right? Then basically one thread is saying we have P threads, and now we are talking of a nested level of parallelism at that point. We say, oh, this thread basically internally is spawning off some more additional threads, but they are all, their scope is whichever thread created that. Just like the master thread created these P threads, a child thread can create grandchildren threads. Sorry, whatever. You can basically go down the layer like that, right? Nested. But nested parallelism is not useful. Okay, so basically you want to limit yourself to one level, because if you are able to do nested parallelism, you should also be able to write the code in such a way that you can do a single level parallelism. And then that's much easier to manage from a strict software engineering point of view. Yeah. Yes.
So in this hello function, we define two variables. One is my rank, the other there are two variables.
Correct.
Are those variables only private to
Yeah.
thread, or is it public to other threads?
So I'll be covering the scope of variables very soon. If you can wait until then, I can answer this question because it's broader. Yeah. So, but that's a very good question. Okay. So I wanted to mainly point to how to set the number of threads, and so we don't have to worry about it. So this line of this region now will execute P threads, and now going back to the sum, going back to the loop, this is what you should be doing. Essentially, you should just say, hey, pragma OMP parallel. If you want, you can use this, set the number of threads ahead of time, and then just specify for, okay? Or you can simply specify the number of threads. I'll let you play with it. So I think you should start, basically code now, so that if you are interested in trying this out, so that you can get the syntax right and get it to compile, we can then move to sum and so on.
So kind of on a higher level interaction with Kamiak, at some point somebody made a decision that Kamiak has what is OpenMP that's going to interact with C and Fortran code so we can parallelize things. And this is basically the application or the process manager that we have at District.
Oh, no, it has MPI.
Yeah, that's not something that all computers know, right?
So we have a number of MPI compilers. So we have MPitch 2, there's a lot of
At least in pitch 2.
By default, when you get into Kamiak, you're loaded with, first, depends on what compilers, you're loaded with Intel. You get Intel full stack that has an OpenMP and OpenMPI built into it. If you do a module load GCC, you'll see OpenMPI, MVA pitch, and MPitch all as under as well. And you're also free on Kamiak to bring in whatever software you'd like as well.
Well, I think, that's great. I just was trying to get my head around, within all of this,
It's not a language, it's a library, right? So you basically have your code already written in C or Fortran. You add lines which are Pragma directives coming from OpenMP library. So you basically use the OpenMP internal inbuilt functions to parallelize your code. Yeah, so your code will continue to compile with I'm going to show you how to compile right now, that will clarify. Yeah. So you're welcome to do this along with me. Basically, I've just commented those lines of code which won't compile, but okay, maybe I should uncomment this one at least and move it here.
So their version should all still be the original dash serial.
Yeah. So
When you close it, you can compile it just fine.
right, yeah. So I'm working on the loop serial.c version. Okay. So all I'm doing is I'm saying OMP set number of threads to this p, and I'm doing some variable initialization, and then I'm basically parallelizing this using the OpenMP parallel for. Okay. So yeah.
Just one quick question, we didn't need to put the brackets after background because the for call,
It's a great question. Yes, we didn't need to put the bracket here because what we have is a single line of code. The for loop, for statement, it's a for statement, right? Statement is one line of code. It just so happens once you go into that, there's a lot of lines of code. That's internal to the for statement, right? So we don't need that. Yes, it needs to be immediately adjacent. No, that won't work. Yeah, unfortunately we need this for, and I'll show you why very soon. Okay, so let us see if I can compile this code. I'm going to use the GNU compiler GCC for C compiler, and let me create the object file, and I'm going to call it loop _p for parallel, hoping that we have successfully parallelized this, maybe not. And then I will link up the library for OpenMP, which is -f OpenMP, no space. So -f OpenMP, no space. Okay, and then the serial code. Okay, so that's what I was little concerned about. Set number of threads I thought must be there. No. Oh yeah, good point. See, that's it's the first mistake everyone makes. Yep. So that's a good process, right, to go through it. So we want to include omp.h. That helps. Yeah, absolutely. Yeah. Please do. Yeah.
You all have your own individual versions,
Yeah.
so nothing that you do will.
Yeah, it will be your local copy that you are using, right? So let's see if this compiles. It does. Okay. So the executable's name that I've created is loop _p. So let me execute it. Okay. Now it's asking for 2 arguments. It says usage is, I've not supplied the required arguments. That's why it's complaining. It says I want to specify the number of iterations as the first argument, and the next argument should be the number of threads. I've specified this in curly brackets and square brackets because this is a mandatory argument and that's an optional argument. But,
Do you
yeah.
want to give people a few minutes to try and take their loop.c
Yes.
and make it parallel?
Yeah.
Just to make sure that everybody's kind of at the next stage before we move on, because you're going to be performance next, right?
Yeah, very soon. Yeah.
Yeah, and actually, yeah, if you do the, if you
Oh,
don't
it's-
have, yeah, it's right here too. If you don't have the -o loop.p, it'll just make an a.out file as executable, so that's just directing what the executable
Yeah.
name is, but you really just need this fopenmp part to make sure that it gets that library.
So there is a default executable that gets created called a.out if you don't specify the executable name. Otherwise, it will be called whatever you want it to be.
So why don't you all open loop.c and let's spend a few minutes trying for you to put in the Pragma and put in the library that needs to be in there.
So don't forget to include omp.h.
Yeah. And then you can put in this part, or use this as a.
Yeah.
And if you get questions at all, just raise your hand. There's a whole bunch of us that are ready to kind of help you watch
So
over what you're doing.
I wonder, answer the question. Minus O option is basically it's saying what is the output executable file name. Yeah, so I just want to make sure. Yeah, it's intentional, yes. Yeah, it's obviously not a right program, so we'll fix it. Because this region of your code is concurrent, so you're writing onto this variable a from multiple threads at the same time, so you could easily corrupt the value of a. So let's not worry about what it does. So I wrote basically perform an arbitrary computation, so I just randomly wrote in a line. No, but we'll come to that, how to fix that. So anyone needs any help, or looks like. Yeah, the reason why I'm not specifying here is because I've specified there. Exactly, yeah. So this for here is saying what next is going to follow is a for statement, and it's telling the OpenMP environment that. And this is the actual for statement. Oh yeah, so OpenMP has support for good reason, but not for while. The reason is while can, whenever you want to specify while, you have the iteration counter or the how many times it needs to execute, right? Internally built in as a boolean. So inside the while code, somewhere you will say, oh, if this condition has been satisfied, I want to exit out of the loop, right? There is no regular computation that happens. In while I can jump in multiple variable steps. From I can do I plus 10 for the next iteration, and then I can do I plus 100, and then I can basically progress at variable rate. So OpenMP can't handle that. No. So for, yeah, no. For is a special case of while. While is more generic. The reason is for progresses in an even step. At every step you are doing I plus plus here in this case, right?
Necessarily, you don't have to code a for where you are indexing.
Oh yeah, but if you do so.
So is there a requirement here that you?
It's a requirement. It's a requirement. Yes. So internally, what you're saying is right. I can tamper with the value I inside the for statement also, but it's good coding practice to then go to the while format and not the for. That's one thing. The other thing is OpenMP will complain if you do that. OpenMP assumes that your loop variable I is extremely important for the parallel for. Okay, so it needs to know how regularly it progresses. That way it knows, okay, there are p threads, there are n iterations, which means I will change from 0 to n minus 1. So I can take the first value of n over p iterations, give it to thread 0, the second values to next thread, and so on. So internally, it tries to do that partitioning, which I'll talk about, the scheduling, which I'll be talking about soon. That's a good question.
Yeah, so he's gonna do that in just a minute here, because we're gonna talk about performance, so then we'll add some statements that specifically show which thread is what and what the time is. Okay, I think we're good to move on.
All right, good. Yeah.
Oh, Lance,
If you didn't put 4 there, but did an extra set of,
If you didn't put what?
if you didn't put 4
Ah,
there,
uh-huh.
but did an extra set of curly braces like you had
Ah.
for a
It
moment,
doesn't, you will have to still specify again OpenMP parallel for, because the runtime library for OpenMP is optimized. The moment you say it's an OpenMP for, it does something different from just a standard OpenMP region. That's why. You can have that, what you're saying, but it will not do what the environment, it's different. Yeah. Okay, great. So, once you have done this, essentially assume that you have been able to compile it using GCC, this line of code. This is the usage, right? And so I'm going to simply do loop underscore p. The first argument is number of iterations. Let me give it 1,000,000. You want to think a little big if you want to go parallel, right? And then let's say 1 thread first. Okay? So what it's basically doing is, this is my output. It's saying the number of iterations is 1,000,000. I wonder what this number is. Oh, that's some, yeah, so I'm sorry. So that, I think that comes from the size of byte or whatever. So we can ignore that. But basically the number of threads is 1. This is n and this is p, okay? And like that I can change the number of threads and run. But we want to look at performance right here. That's what we are trying to really optimize. So what we want to do is, we want to put a timing function to understand what the timing would be if you use 1 thread and 2 threads and 4 threads and so on. Okay? So to put the timing function, typically OpenMP also has its own inbuilt timing function which we can use. Since we have omp.h included, we can use that. So I'm going to use that. I'm say double time, time is a double, and simply call this function omp get w time for wall clock time. Okay? So this function essentially returns the current time, wall clock time, and puts it in this time variable. And this I am doing before the paralleled region. And once the paralleled region completes, I'm going to call the function again. So I'll say the total time that it took, time equals omp my current time get w time minus my old time, right? And then I will add I'll add a print statement here, printf, right? Total time, right, equals, it's a double, so percentage %f I'll use, and seconds. All right. So let's focus on time first, not the semantics. What happens to A we will see later. But let's at least see whether we see speed up or not. That's what we are after really, right? So you can actually type this.
So what is that return? Seconds?
Seconds, yeah.
If you do it initially,
Mm-hmm.
what is the basis of the time?
Oh, so it's saying this is T1, this is T2. No. This is just some time, right? The current time, and this is the current time as of this line of code, right? So essentially, T1, T2, T2 minus T1 is the time that has elapsed.
Some arbitrary
Yeah, it's basically the, yeah, arbitrary epoch, as long as it's really recording the time that has elapsed from here to there, right? So this is basically recording the time as of this line. This is recording the time as of this line, so you subtract the old time from the new time, you get the difference, right? That's how much long it took from here to there. Yeah.
just because you're skipping ahead a little bit, I don't
Yeah.
know if you want to move forward on the slides at all. This does have this nice template that everyone now said. See what I mean? Yeah. So for those of you guys, as we move forward, you're going to be parallelizing a couple codes, right? So here's kind of like a template of how you can do that. So this has the OMP.h.
And we already discussed
And
this.
you've already discussed this. And so then,
Yeah, we will come to the scope very soon.
okay,
Yeah,
perfect.
yeah. So let's record the time. Okay. So once you have done this, let me do a compilation again. So GCC minus loop p, whatever. Okay. Now let's run a million iterations using one thread. It records, it shows some time, right? This is 5 milliseconds, 5.8 milliseconds, whatever that is, right? And then let's say I want to run it on 2, the time has actually gone up. Yay! Is that what you expected? Let's run it on 4 threads. The time has kind of stayed, it's about the same as 2 but equally bad, right? Let's use 8 threads. I'm just doubling the number of threads. The time has actually gone up again. We thought we were going to reduce time, not increase time. So what's happening here, right? That's where the scope of the variables come into play. Okay, so now let's go back into your code and ask, why did we not see an improvement in time, decrease in time? Because the more threads run, the less time it should take. Double the number of threads should ideally half the time, right? But here the time is going in the opposite direction. So to understand that, we have to now understand what are we doing inside the loop, right? So as you can see, there is this, we are using really one variable inside the loop, this variable called a. And this variable is a shared variable. By default, the scope of a variable as it enters an OpenMP region is shared, meaning all the threads will get to see that, one copy of that variable, okay? So which means they are competing to access the same memory location from different directions. And that slows actually your process. It doesn't speed things up but slows things down, right? In fact, it's dangerous to do this because the same variable a, if it is on the right hand side of the equal sign, we are good. At least they are reading, multiple threads concurrently reading is fine. But here the a is on the left hand side, which means they are writing at the same time, and that could possibly mean one thread fills up, a is an integer, it's 4 bytes, one thread fills up the first 2 bytes, the second thread fills up the next 2 bytes. The data is corrupted, it won't make any sense. We'll talk about synchronization for that. But let's at least get the scoping right. So to at least get the scoping right, is this what we want to be doing? Well, a is because is being written to, let's assume that it's okay in this context to make the variable a private to every thread. We don't want it to be shared but private. What that means is each thread will make a separate copy of a and operate on that copy of a. So your a and my a are 2 different a's. Okay, then we don't have to go into the same and look for the same memory location. So I'll specify that by saying private a after the for, saying here comes a for loop. Inside that for loop, I am using this variable a using the private scope. Okay. So now we have specified the scope, which means that a is now will be treated as a private variable for each of those threads. All right. But remember, the threads are themselves executing multiple iterations. So within each iteration, a copy of thread, a copy of this variable a is going to be different from the copy of the same variable a in another iteration. Okay. So it's not like each thread gets a separate copy, but each iteration gets a copy. Because each iteration is executed by at most one thread or exactly one thread, it becomes a private scope. Make sense? Okay, so that's all I did. Let's save this and compile it, and let's see what happens to the time. Okay, one thread is 5 milliseconds, 2 thread is 2.6 milliseconds, 4 thread is 1.4, 8 thread is 1 decimal place shorter, right, 0.9. Time is decreasing, that's a good sign, right? Now we have to ask, is it good enough? Is it the best you can do? right? But time is improving, right? So for one thread, the one thread run and the two threads run, this is half of that, right? And this is not half of it, but it's okay, right? It's still reducing. Now half of it would be like 1.3 milliseconds as opposed to what is here, 1.4 milliseconds, right? And this should be 0.7 millisecond as opposed to 0.9 what it is. So we are not getting the best possible, because when you double time, your time should half. Double the number of threads, the time should half, right? But we are observing something that's less than that. So